Thank you very much. Good morning, everyone. Today we're going to be taking a look at poll investigations using Neo4j. First, we'll talk a little bit about what the poll data model is, for those who aren't familiar with it. We'll spend a little bit of time talking about why Neo4j is such a great fit for projects that use the poll data model. Then we're going to dive right into a live demo. We're going to run some Cypher. We're going to take a look at the Neo4j browser and investigate a sample poll data set. When we're through with that, we'll take a look at some sample data visualizations. We have two different presentation layers to show you. One is a custom-built application by one of our colleagues here at Neo4j, and the other one are some visualizations using Tableau Public. And then we'll wrap up by talking about how you might extend the demo, in the real world, what it might look like beyond just the demo use case. And then, as Angelica said, we'll have some time at the end for Q&A. So what is the poll data model? So poll stands for persons, objects, locations, and events. So this data model is quite common in investigative use cases, policing, things like that. Some of the varieties of persons you might encounter could be victims of a crime, suspects of a crime, witnesses to a crime, things like that. Events obviously could be crimes, but they could also be arrests, meetings between persons, phone calls, transmissions of data, and so forth. Objects could be things related to those crimes, maybe a vehicle, maybe some evidence, a weapon used in the crime, documents associated with the case, things like that. And then in terms of locations, you can have the crime scene, you might have a person's home address, you could have their work address, and so on. In terms of use cases for the poll data model, as I've mentioned, policing is a big one. You might also see poll used in counterterrorism, border control and immigration, social services, and child protection, which will actually form part of the demo that we take a look at later. Missing persons use cases, if you're trying to investigate who might know someone who's gone missing, where they typically can be found or where they've been. And I've even seen the poll model used in prisoner rehabilitation use cases, where maybe if someone is on parole, you're trying to help them not reoffend, turn their life around. You might want to know who they've offended with in the past. Are they a member of a gang? What sorts of places that they should and shouldn't be going because they might be running into people that they've offended with in the past, and so forth. So there's quite a few different use cases that you can apply the poll data model to. So the question we get when we do this demo a lot is, what about Big Brother? Why would we want to be enabling this sort of surveillance? Why would we want all of this data to be concentrated in one place? I think it's you have to be kind of realistic about it, right? Some of the use cases we've looked at, counterterrorism, preventing crime, are certainly very worthwhile, uses for this sort of data. We already give up a lot of what you might consider your privacy. There's CCTV, at least here in the UK, all over the place. We leave a digital trail every time we use social media. We watch YouTube, we send emails. So I think, we're not really here to say what's the right use of these and what isn't by law enforcement. But I think there's a balance to be struck, and as long as we can trust that our data is being used appropriately by the police forces and government agencies, then certainly you can see how applying something like the demo we're going to see can actually bring about a lot of good for society. So quickly, we'll talk about why Neo4j and why Neo4j is such a good fit for the poll data model. As we saw before, taking a look at the overview of the poll data model, and as we'll see a bit more in the demo, these sorts of use cases are all about the relationships and connections between data. Having a list of people and a list of locations and a list of events in isolation isn't very useful if you're trying to do a crime investigation or prevent a terrorist attack. what you want to know are the connections between those things, the connections between people, the connections between those locations. And Neo4j is the #1 database for connected data. It's built from the ground up as an enterprise-grade native graph database for traversing those sorts of connections between data at depth, in real time, and at scale. And hopefully you'll get a sense for that if you're not familiar with Neo4j already as we go through the demo that we'll see shortly. Using those connections in real time is what really helps Neo4j shine and helps move these sorts of use cases from simply representing a static view of data that already exists, moving it up the value chain to actually generate insights, right? So away from just reporting what's happened, being able to predict what's going to happen, and actually use these tools to solve problems in real time. And so being able to do that all in one database, in memory, in a unified architecture is really critical. If you were to try to apply the same techniques we're going to use in the demo to a relational database or to another type of NoSQL database, you probably are not going to get the same performance. You're not going to get the same ease of use if you're having to traverse different data sets across different machines in different formats. So without further ado, we'll dive into the demo. Just to give you a bit of flavor for how we built the data set, there's freely available data on the web for UK street level crime. So I downloaded some of that. In particular, we're going to be looking at crime from the Greater Manchester Police Force for the month of August 2017. So not to pick on Manchester, but it was a good sized data set, nice and varied, and I thought it would make an interesting demo. The crime data, since it's freely available on the web, obviously isn't too specific. It doesn't include data about real people. What it does provide are unique crime IDs, the longitude and latitude for the crime at the street or block level, which becomes really important when we take a look at mapping that, looking at the data in a geospatial format. It provides the month, the crime type, and the last outcomes. Since it didn't include personal identifiers or a real great level of detail in terms of the exact time of the crime, some of that was randomized. So we created random people, random officers, random phone calls, things like that to add to the data set. And then we took the longitude and latitude and translated that to UK postcodes using public APIs. So it is in some sense real data. It will look real as we go through it, but it's not super real. So don't be worried. We're not actually going to be looking at real people. In terms of node counts and relationship counts, there are almost 15,000 locations that are loaded into the data set. That represents almost 29,000 crimes. There's 105,000, almost 106,000 relationships between all the different nodes. So it's not a huge data set by Neo4j standards, but it's certainly big enough to allow us to do an interesting demo and get some interesting insights. So I'll switch over to the Neo4j browser and we'll have a look. So hopefully some of you are familiar with the Neo4j browser. This is the developer tool for investigating a graph and being able to visualize a graph. We'll take a look first at the data model that we built for Pol. So you can see here in red, there's persons, there's locations in purple, there's crimes in blue, which represent events, and then there's objects in pink. So we have some generic objects, and then we have a specific vehicle type that is loaded into the database. We're probably not going to actually take a look at it during the demo, but just to give you a sense of how we might model some of the different object types. We also have phones, phone calls, emails. Locations are further broken down into postcodes and areas to allow us to group things together by nodes. We have officers in gray, so we can see who might be investigating particular crimes. And then we have a bunch of relationships between people. So at a high level, we have just knows. One person knows another person, and that's just a generic relationship between any two people that know each other. And then we have some more specific relationships. Someone might live with someone else. Someone might know someone else through their social network. Somebody might be a family relation. And we might know that somebody knows somebody else because we have a phone record that indicates they've called that other person. And then between people and crimes, we have a generic party to relationship. We're using that as a proxy for someone who is involved in a particular crime. But we'll talk a little bit later about some of the other relationship types that you might relate between a person and a crime. So again, just to review some of the data that we have in the database in terms of crime types. The top crime for Manchester in the month of August 2017 was violent and sexual offenses, followed by public order, criminal damage and arson, and so on down the line to possession of weapons, which was the smallest number of crimes at 236. If we want to take a look at the top locations for crimes, perhaps no surprise, Piccadilly, which is the area in Manchester for the main train station, is the top location for crime events, followed by a shopping area and a nearby prison. And then moving on down, it's not until you get to 43 Walker's Croft where you start to get some residential looking addresses. So high amounts of crime in public areas, nightclubs, supermarkets, things like that, perhaps not unexpectedly. And then residential addresses seem to have smaller amounts of crime. Then we have a little bit of fun with the data. So anybody here in the UK probably knows there's a soap opera on television called Coronation Street. Coronation Street is shot in it's meant to take place in a fictional neighborhood in Manchester. And there's actually a Coronation Street in the address, in the data. So one Coronation Street, which in the television program is the home of the Barlows. We can take a look because we have the longitude and the latitude for that address. We can do a geospatial search and look for other addresses that are nearby where crimes have been committed. So we're looking for addresses within 500 meters of one Coronation Street where crime has taken place. We can see there were 3 crimes at that address on Coronation Street. 104 meters away at 158 Gloucester Street, there was 1 public order offense. At 147 West Crown Avenue, which is 162 meters away, there were 3 crimes, a mix of public order and shoplifting, and so on and so forth. We'll take a look a little bit later at some other uses for geospatial. It's quite, I think, an interesting way of working with the data here. And then again, one more bit of fun with the data. Another television program here in the UK is Inspector Morse. There is an Inspector Morse, Chief Inspector Morse in the data set. So here we can take a look at all of the crimes that are being investigated by Chief Inspector Morse. So you can see he has quite a few crimes associated with him. If you wanted to, you could navigate through them. So here's a burglary that's being investigated. That burglary took place at 175 Somerset Close. There don't seem to be any people who are associated with that crime yet. So if we take a look, if you see at the bottom of my browser, the very bottom, as I hover over that burglary, we can see that the last outcome was investigation complete and no suspect was identified. So unfortunately, Inspector Morse was not able to solve that burglary and the culprit remains at large. Right, so we'll move on to taking a look at what a sample drugs investigation might look like on top of the POL data model. So we're going to start by looking at another officer who's in the database, Officer Lee Reeve, to see what crimes are investigated by Officer Lee Reeve and have the last outcome of under investigation. So this would give us crimes that are still open in terms of the investigation. And we can see that Officer Lee Reeve has a number of crimes that they are investigating. There's some criminal damage, public order, some other theft, and 3 drugs crimes. So if we're interested in drugs crimes, what we can do is click through those, expand the graph a little bit, and see what's going on. So here we have some objects in pink. We can see there's some evidence looking at the bottom of the browser. This is 3,500 pounds in currency, and then 43 cannabis plants and 3 kilograms of prepared cannabis as evidence. So here in the UK, cannabis is illegal. The charge that's being investigated here is the production of cannabis with the intent to supply. So this is an investigation of a drugs dealer and a drugs manufacturer. The person who's associated with this crime, who's party to it, is Raymond Walker. And we can see the crime occurred at 151 Mottram Street. Then we can take a look at some of the other drugs investigations for Officer Lee Reeve. Both of these drugs offenses happened at the same address, 23 Bodmin Road. Here we have some packaged cannabis and some more currency. We have Jack Powell, who's associated with this crime, party to this crime. And then if we expand the other one, we can see there's some more evidence, some more cannabis, some more currency, and a scale. So these things put together, could indicate, the intent to distribute cannabis, which I think is the charge, possession of cannabis with the intent to supply. And this Jack Powell is party to both of these crimes. Okay, so we could navigate through the graph like this, pointing and clicking and seeing what else we can find out. But at this point, it probably makes more sense to jump into a specific query. So what we can do is see if there's a relation between the 2 people who are related to the crimes that we just looked at. So we're going to look for the shortest path between those persons and see what comes back, see if there's any kind of a network between them, so we can start to associate the person who's producing drugs for sale and the person who's actually selling them potentially on the street. And it turns out that there is. So we have Raymond, who is the gentleman associated with the crime for production of cannabis, and Jack Powell here on the right, who is suspected of possession and intent to supply. And we can see there's a little social network that sits between them. If we can explore that a little bit, we can see there's a family relation between Brian and Jack. Brian is Jack's dad. Brian lives with Philip Williamson. And then it turns out Philip is the father of Raymond. So Jack's father lives with Raymond's father. So there's a pretty good chance then that they've come into contact with one another. There's also a number of other links between them. So Raymond has a sister, Kathleen. Kathleen knows Alan. Alan is Jack's brother. And then there's a bunch of other relationships that sit between them. So there's a pretty good chance now, we think, that maybe Jack and Raymond know each other. And maybe we can start to build a case that says Raymond is growing cannabis, Jack is getting that cannabis from him, and then Jack is selling it on. Now, what we can do is look at those individuals again and say, are there people in the graph around them who are also associated with drugs crimes? So can we start to loop in more people into this social network who are also associated with drugs crimes? So here on the right, we have our officer and the 3 drugs crimes in question. We can see Jack, and we can actually see Jack is associated with some more drugs crimes. So there's more possession of cannabis and possession of cannabis with intent to supply charges. But because those aren't associated with our officer, they would be linked to another one, presumably. So here we have Officer Hellwig, and here we have Officer Bullen. So our officer, Officer Lee Reeve, would probably want to be in touch with those officers to find out a little bit more about these drugs crimes that Jack is related to. Here's Raymond's. We can see there's some new people associated with drugs crimes here. We have Brian, who we saw in the last graph, who is Jack's dad. So he has been associated with some possession of cannabis charges. And then we have someone new in the graph, Diana. And Diana is also associated with possession of cannabis with intent to supply crimes. Diana, let's see, Diana has, Diana's mother, Jessica, also lives with Brian. And she knows Philip. So it's pretty easy to then start building a case that says Diana knows Jack. Diana lives with Raymond's sister, Kathleen. So you can start to build a map of people that you would want to question, people that you might want to watch, and start to build a case around how these individuals might be associated together as part of a drugs network. Okay, so now we're going to move on from looking at drugs crimes to looking at some queries around vulnerable people. So this is more along the lines of the social services child protection use case that we mentioned at the beginning. We're defining vulnerable people here as people who are in our graph who are not themselves associated with crime, but who have friends who are associated with crime. And the more friends you have that are criminals, the more at risk you are, right? It means that you might get involved in some of those crimes, you might be exposed to harm, and especially if you're a child, that might be a case where social services or the police might want to get involved. So we can see the top result is Anne Freeman. Anne has 8 dangerous friends. Then there's Bonnie Gilbert, who has 7, and so forth. The thing we can do here quite easily, which is kind of a really powerful feature of the graph, is that we can start to say very easily, well, what if I'm not just interested in their direct friends, but the friends of their friends? Start looking for a wider social network that might be exposing these people to crime. So here we see if we go 2 hops out, the friends of people's friends, we can see Anne Freeman is still in the lead. She now has 10 dangerous friends or friends of friends. Bonnie Gilbert has 8 instead of 7. And then some of the names are starting to change down here at the bottom. So Anne Fox, who is not in our original list, when we look at her extended social network, she now has 7 dangerous friends or friends of friends. And you can keep doing that very easily just by changing that number in the query to look at the friends of their friends of their friends, right? At which point the results change pretty significantly, right? Walter James has 18 dangerous people in his extended social network, looking 3 hops out. So this is a really powerful feature of the graph and something that Neo4j does really well, whereas in a relational database or another data model, doing something like that would actually be a little bit trickier. You would have to look at some recursive queries. You'd have to start following joins several layers deep, and you wouldn't get the same sort of performance that we did here, where we were able to change the query and get the results back just as quickly 3 hops out as we were 1 hop out. So going back to the original set of results, we can now take a look at the graph for the most vulnerable person that we found, Anne Freeman, and take a look, just verify visually. Here's Anne. She's not associated with any crimes, but she has this network of friends who are around her, and each of them is associated with a crime. So Craig is associated with some public order offenses. Maybe he likes to get in fights or get a little too drunk at night. Victor is associated with theft. There's a few robberies. So dangerous friends, but perhaps not as dangerous as they might be if it were violence or sexual offenses. It might be something that would raise even bigger alarms. And we can do the same thing. We can take a look at her extended graph. Friends of friends. So now, in addition to the original people that we saw, we now get Billy, who's associated with some vehicle crimes, and we get Andrea, who is associated with violence and sexual offenses. Now, if we'll take a look at this one first. So maybe we'll say, okay, Anne Freeman has these dangerous friends, but the ones who put her at the most risk are the people who live the closest to her. So what we're doing here is taking a look at Anne Freeman and looking for her friends that live in the same area as her. And we can see she has one friend, Craig Marshall, who does live in SK1, so in the UK. The first part of your postcode is usually at the neighborhood level, so SK1 would represent a specific area of the city, and Craig lives at 51 Henry Street, 63 Hanson Mews is Anne's address. They both live in the same neighborhood, and Craig is associated with public order offenses. So you might want to look at that relationship with Craig, or you might want to keep an eye on Craig if we think that he's going to do or put Anne any harm because they live so close to one another. And then lastly, looking at this list again, so this list of the top 5 people with the most dangerous friends, what we're going to do is look at the paths between them. So we can say, what is the shortest path between each of them? Do they know each other at all, or do they operate in the same social networks? So in Neo4j, quite easy to do. We don't have to specify how we want to find those connections. We use this function, the shortest path, between any of these two people, following the nose relationship to any depth. And then this is what we get back. So taking a look, we can see Kelly Peterson was in the graph. She knows Anne Freeman by a mutual friend, Amanda. Here's Bonnie. We can see that there's 4 hops between Anne and Bonnie. So maybe there's a chance they know each other, but 4 relationships out is pretty high. So maybe they don't know each other. Here's Bonnie and Annie. That's how they get to Kathy. So you can build a picture of the graph, the relationships between individuals, and then try to understand how likely it might be that they know each other or that they operate in the same social circles. Okay. Now we're going to look at the list of dangerous friends and individuals a little bit differently. So now we're going to take a look at vulnerable people who are vulnerable because they have relatives who have dangerous friends. So this might be even more important if you have children. Are their parents hanging out with criminals or their brothers and sisters? That might put them at more immediate risk than an extended social circle. So it's a very similar query, but first what we're doing is looking for people who have relatives who have friends that are associated with crime, but the individual and that relative themselves are not directly associated with crime. We get a different list. Kimberly Alexander comes back as the person who's most at risk, followed by Walter, Henry, Andrea, and another Kimberly. But then we want to modify the query a little bit. So not only might it be important that this relative has dangerous friends, but we're interested in people who live with that relative who has dangerous friends. So this would say maybe there's a child whose parent or whose brother and sister live with them, and if they're bringing criminals or suspects into the house, that puts these people at even higher risk. in which case there's only two of the people in the graph that meet that description. So there's Kimberly and Martin, who live with a relative, and that relative associates with people who are party to a crime. And we'll take a look quickly at the graph for Kimberly Alexander, the top person in the list, who has 7 dangerous family friends. So here's Kimberly. Looking at the bottom there for the graph, the age property that's set in the graph, Kimberly is only age 12. She lives at 53 Ridge Grove. This is her parent, Bonnie, and Bonnie has a number of friends that she knows through her social network or has made phone calls to who are associated with crimes. So there's a lot of vehicle crimes going on here. Criminal damage, violence, and sexual offenses for a few of these individuals. So this might be an alert or certainly cause for alarm for the social services or for the police. And if they're interacting with Kimberly and Bonnie already, then this might be something that they would want to address or investigate further. Okay. So moving on then to our last section, we're going to take a look at some graph algorithms against the poll data that we have in the graph here. So Neo4j have written and published a number of graph algorithms. These are algorithms that are quite specific to working on the graph. A number of them are very common. PageRank, for example, which we won't look at today, but which is an algorithm that's used by Google to help drive their search results. So we're going to take a look at 2 of the algorithms today that are useful in the context of poll. One is triangle counts. So the triangle count algorithm, what it does is looks for triangles of relationships in the graph. So person 1 knows person 2, knows person 3, who knows person 1. Yeah. And this is a commonly used algorithm in the context of social networks because the incidence of these triangles is much higher than it is in a random set of data. So it helps to understand social networks, quantify social networks, and cluster groups together. So we can see here, Deborah Ford is the top result in the list. She's part of 10 different triangles, followed by Philip Perry, who's 8. Who's 9, Peter Bryant, who's 8, and so forth. So it might help explain this a little more visually by running a query and taking a look at Deborah Ford and the triangles that she's part of. So you can see in the query here at the top where Deborah Ford knows person 2 knows person 3, and that person 3 knows Deborah Ford. And we're not following the direction of the knows relationship. We're ignoring it, so it doesn't matter in what direction that knows relationship is stored in the graph as long as those people know each other. Okay, so here's Deborah. We can say there's a nice little graph around her. And so this is each one of these is a triangle. So Deborah, her mom, Patricia. Patricia is also the mother of Jonathan. Jonathan is the sibling of Deborah. So this represents one triangle, right? Deborah, Brandon, and Philip is another one. So each one of these is a triangle, and there are 10 triangles that sit around Deborah in total. The interesting thing you can do here then is start to infer new relationships that might not be persisted in the graph. So, for example, we saw Patricia is the mother of Deborah, is the mother of Jonathan, and Deborah and Jonathan live together. But looking at the graph, we can see Deborah also lives with Harry. Jonathan lives with Harry. Deborah lives with Peter, which means Jonathan also lives with Peter. So Deborah and Jonathan live with quite a few other people that Patricia, their mom, is not directly linked to in the graph. But you might say it's probably pretty common for a mother whose two children live together to maybe have at least met some of their roommates, right? So you can start to infer relationships that aren't necessarily persisted in the graph or haven't been recorded already. You might then be able to create a new inferred relationship between Patricia and Deborah and Jonathan's roommates to at least say that it's likely that they've met or perhaps they know each other. So that was just looking across the whole graph at people that happen to know other people. What we can do now is run the same triangle count algorithm, but in this case, instead of doing it across the whole graph, you can see here that what I've done is run it against a subset of the graph. So we're interested here in people who have committed a crime and then know other people who have committed a crime. So we're not looking at the whole graph, we're looking at a subgraph and looking for triangles of people who all have committed crimes potentially together. Okay. And here we can see Philip Williamson is part of 4 triangles where each of the people in all of those triangles is somehow related to a crime. And then there's Alan Ward, who's 3, and so on. So we take a look at the graph for Philip Williamson, the person with the most triangles from that last query. We can see here all the people who are part of the triangles with him. Here's Philip. Philip is related to 5 vehicle crimes. This name looks familiar. So this is Raymond Walker, who we looked at the beginning of the demo, who's related to a drugs crime. He's also related to a vehicles crime. Here's Brian Morales that we saw before as well, a number of drug crime and vehicle crime. So there's a lot of vehicle crimes here in the social network that sits around Philip. So what we could be looking at here could be a gang, a network of criminals who specialize in vehicle crimes, maybe vehicle theft. So this might be something that could then, be added into the investigation for those crimes or built into a bigger investigation. And it's interesting that the algorithm has found a lot of the names that we already found manually by digging through the graph earlier, right? So it sort of validates that the manual investigation exercise, but also shows how you can use the algorithms to automatically start finding these clusters in the graph. And then lastly, we're going to take a look at the betweenness centrality algorithm. So what this is going to do is going to show us the person in the graph who sits on the shortest path between the most other people. So this is one measure of centrality or importance in the graph. This person is connected highly to a high number of other people, and the person or the node that sits on the shortest path between the most other nodes is often a bridge or at least a path for movement of information, communication, or goods, something like that through the graph. So if we run that, we can see Annie Duncan scores the highest, followed by Anne Fox, and so on. So there's 25 results that we got back. These are the 25 most central people in our graph. And then if we take a look at the graph itself, I've only gone 3 levels out at this point, although the algorithm did run across the whole graph. To visualize the whole graph in one go on the screen is quite a difficult thing to comprehend, so it's a little bit easier with just 3 hops to get a sense. Here in the middle, this is Annie Duncan, who scored the highest in the results. And you can see there are a number of maybe groups, a number of smaller networks that sit on the edges of the graph that would move through her in their connections to other parts of the graph. So we can see Annie is fairly well connected, even at only 3 hops out. And of course, if you were to investigate farther out in the graph, you would probably find that, while difficult to understand visually, would be even more true when you can see all the different relationships that she sits between. Okay, so that's the end of the demo in terms of Cypher and the Neo4j browser. We'll take a quick look at two ways of visualizing this outside the browser. So the browser is really great for developers and users who know Cypher, but if you want to be able to expose some of this data maybe to business users or you know, in a more easily digestible format, there's a number of different ways you can do that. So we'll take a look at two. One is an example front end designed to give you a feel for what it might look like if there was an application written around poll investigations for an end user. So this, as I said, was designed by our colleague Case. It was built using Spring Boot, ZK Server, Font Awesome, Iconics, and Viz.js. After we take a look at that, we'll also take a look at Tableau. So I've created, I've created a few sample visualizations that we can take a look at. This is using Tableau Public, so it's not the full version of Tableau. This is kind of the free version that I use to do quick mockups. The connectivity between Neo4j and Tableau Public is managed by the Neo4j Tableau Web Data Connector, which is available on GitHub. And it's really just a way of seeing what types of BI visualizations and geospatial visualizations you can do on top of the data that we just saw. So first, the poll investigator dashboard. You can see this is really just a mock-up, the sorts of things that somebody who is investigating on top of this poll data model might look at. There's a crime map, which shows the locations that we've been looking at. It's here on the left-hand side. We've got a limit, so we've said only show us locations that have 35 crimes or more. You can see those locations on a map and navigate them quite easily. It's got a lot of the reports that we looked at already. So it's got officer investigations, which we saw. There's crimes near locations. So this is our Coronation Street example. You can see on the left where we've got query parameters. We're looking for crimes within 300 meters of the Coronation Street address. So rather than having to write Cypher, edit Cypher, this is a way of providing a front end for people to enter in the parameters they're looking for and then be able to get the results back. So if we look on here, Coronation Street is here. We can pull that around as we want to. We can click through it just like we did in the browser to start to see some of the other nodes that are associated with it. So a nice way of giving someone the ability to investigate the sorts of crimes that are happening around a particular location. And then just to give one more example from this front end, if we take a look at this Connect tab, what this allows us to do is search for individuals and then look for ways that they're connected, sort of like we did before with the vulnerable people. This has got a nice autocomplete feature. So we've typed Gilbert. We can see here's Bonnie from our results before. If we highlight her, we search for another individual. So maybe we look for Kelly Peterson, click on the connect button, and that will run the shortest path query for us. You can see here's Kelly, here's Bonnie. We can see that there's a social network between them, a fairly long one. So Bonnie knows Billy, Billy knows Lillian, Lillian knows Anne, Anne knows Amanda, Amanda knows Kelly. Then we can also see Bonnie knows Kenneth. Kenneth lives at Greenhurst Road. Kelly lives at Alder Close. They're both in the same neighborhood. So while it's probably less likely, there's a chance as well that they know each other just because they live relatively close to one another. So a good way of being able to give someone the ability to do the shortest path quite easily between two people that they search for with this nice autocomplete feature. Okay. In the interest of time, we'll move on as well now to Tableau. So here's the first of the visualizations that we put together. These are all of the locations that we have in the database that have crimes associated with them. They're plotted against the map. And what I've done is associated both the size of the circle for the location as well as the color of the circle for the location with the number of crimes that have happened there. So the smaller the circle is, the fewer crimes have happened at that location. The bigger the circle, the more crimes have happened. And also it uses sort of a red, amber, green color coding where green circles on the map have fewer crimes associated with them. And then here's Piccadilly, nice big red node, which was the location in our graph that had the most crimes associated with it. So because we got the longitude and latitude for the crimes, it allows us to do this sort of geospatial representation, which is always, I think, quite powerful. You know, it lets you kind of drill down to the street level and see where things are happening and what's happened close to what else. Then, as you might expect, it's also fairly easy to put together a chart of crimes. So here we have all of the crimes that have happened for the month of August with their numbers. We can see here violence and sexual offenses, as we saw at the beginning, has the highest number of crimes. Here we've charted it by day. Fairly straightforward chart, but still interesting. For example, we can see here in the UK at the end of August, there's a bank holiday weekend, right? So we can take a look from the 29th to the 31st of August. We can see that, interestingly, violence and sexual offenses has dropped, but public order offenses have gone up, right? As have some of the other crimes. So, you know, an interesting way of seeing how the crimes in our graph change over time. And then last but not least, I think this is probably the most powerful combination of the Tableau demo and graph demo that we have today. This is a map of the centrality, the between the centrality algorithm that we saw earlier. So each one of these circles represents one of the 25 top people in our between the centrality results. So these are the people that are by that rating the most central to our graph. There's Annie Duncan, who we saw earlier when we took a look at. Again, the smaller the circle, the lower they are in the ranking, and also the greener they are, the lower they are in the ranking, whereas the bigger, redder graphs are the most central people in the graph. And this, I think, is quite interesting because when you're looking at it in the graph results, you can see their rating, but you can't necessarily see very easily where they are, you know, actually out in the world. And by looking at it this way, we can start to see actually there's some clusters. So these three individuals here are very close to one another, right? So within the top 25 people in the graph, to have that many people so close to each other could represent some sort of association between them, right? Again, over here, there's another cluster. Someone who's one of the most central people in the graph, Amanda Alexander, lives quite close, you know, within a few kilometers of two other people that are central in the graph. So that might represent, you know, another group. And here we have, you know, within 5 kilometers of each other, a much bigger cluster of individuals. So again, not proof that they commit crimes or that they know each other, but certainly worth looking at, right? If a number of the most central people in the graph live that close to each other, it's certainly worth more investigation. And I think by combining the outcome of that algorithm with the geospatial representation in Tableau gives you that really powerful view, you know, that could certainly lead you on to further insights. Okay, so that represents the end of the demo. Lastly, we'll talk about how the demo could be extended or what it might look like in real life compared to what we just saw. So you might want to use, instead of persons for the P in the pole model, you could use personas. And that could represent aliases, right? A way to add nuance and group people together in the graph if you think they might be the same person. I mentioned before, you might want a richer set of relationships. So rather than party to a crime, you could have witness to, victim of, suspected of, convicted of, and so forth. Some really important things to add in a real life version of this graph would be traceability and auditing. You'd really want to understand how that data found its way into the graph, how you know that it's reliable, who put it in there, and did they have the right to know that information? So coming back to our big brother topic, you really have to be able to demonstrate in real life and real policing cases how you got the information that you have, how you know it's true, and where it came from. You'd also probably want some security configuration in there, so you'd want to limit who can see what in the graph. You know, in a policing context or an anti-terrorism context, you might only want certain individuals to know who's associated with a particular case or particular nodes, especially if there's someone who's undercover, you know, or you know, witness has come forward. You might not want that witness's identity to get out, so you really would want to control access across the graph. You might want to add weighting to some of the relationships. So just in the examples we saw before, knowing someone through a social network might not be considered as strong a relationship as living with someone or being related to someone. So you might want to be able to weight those relationships as you follow them and follow the most important ones. And you might also want to weight certain offenses. So shoplifting might not be considered as serious an offense as a violent or a sexual offense, certainly in the context of the vulnerable individuals we saw before. And then lastly, there would be much more data. Neo4j is really engineered to operate at very large scales. So, you know, you would expect there to be millions or billions of nodes representing all sorts of people, objects, locations, and events over a large number of time in a large area in the UK. So while what we looked at today was of a reasonable size, certainly in real life, you would expect a massive graph, but you would expect to be able to work with it in exactly the same way that we did today. So I'll open up the floor to questions and answers.